Today we have with us Professor Ingrid Daubechies, and it's a great honor to have you here. Thank you so much. So Professor Daubechies did her PhD in Brussels and then spent most of her career in the US, where she is currently a James B. Duke Distinguished Professor of Mathematics and Electrical and Computer Engineering at Duke University. She's one of the world's leading experts in the theory of wavelets, and one of the things she's most well known for is for introducing a family of wavelets that are very widely used, for example, in image analysis, and yes, they now bear her name. So for example, her work was one of the key components of the JPEG 2000 compression standard. She has more prizes for work than I can possibly list here, but as an example, she has a MacArthur Fellowship, a Leroy Steele Prize for similar contribution to mathematical research, and just this year, she got a Princess of Asturias Award. She's a fellow of the American Mathematical Society and the American Academy of Arts and Sciences, a member of the National Academy of Science and the National Academy of Engineering, and she was the first female full professor of mathematics at Princeton and the first female president of the International Mathematical Union. So yeah, thank you so much for being here. The last thing I need to mention is that the current issue of Eureka is available. So yes, if anyone wants a copy, please do get in touch with the committee. But yeah, over to you now.
Okay, well, thank you very much for asking me to give a presentation. If there's a question that is best answered while I'm talking, please don't hesitate to let Yuri know, and he can then interrupt me for the question to be asked, because I mean, as I always say, I know everything I'm going to say. It's really for your benefit. So if you get lost because I'm not clear, I'd rather clarify that than just drone on. Okay, so let me share my screen, and I hope that will work well. So I'll go to presentation. So I hope you should see the title slide now. Is that working? Yes. Okay, great. So, I have been working on, I like working with people in other fields. So I have worked myself with people in neuroscience, in geophysics, and I've now a very active collaboration with people in evolutionary anthropology. And of course, I've worked on the mathematical theory of image processing and image compression. I still do that. But one of the collaborations that started maybe 15 years ago that has given me a lot of joy is working with people who are not even in the sciences, but people in art history and art conservation. And so I'd like to tell you about that in this presentation. And I'm going to start with examples that actually are not based on my own work, to show that, in fact, there are instances of mathematics being useful for art history and art conservation. Art conservation, of course, everybody knows, relies a lot on physics, X-rays of paintings and so on, and on chemistry, analysis of the different materials used. But applications of mathematics are not so widely known. So the very first one is work by Massimo Fornazier, who is a professor in Munich now. But the work I'm going to talk about was work he did while he was still a graduate student, which I believe is called postgraduate in England, meaning he was working on his PhD. So then I'll talk about thread counts, and then I'll talk about my own work. Okay, so Massimo Fornazier worked on reconstructing frescoes in the Eremittani church in Padua. So this is the Eremittani church, which at the end of the Second World War looked like this. It had, in the very final weeks of the war, been mistaken for a military target and been destroyed in bombing. And this church, which was known for world famous frescoes by Mantegna and others, that were shown in, this is a virtual reconstruction of one chapel. Again, virtual reconstruction in which only the bottom fresco is one that was preserved. It was preserved in the bombing because it was not there. I mean, it had been removed for conservation against moisture. You see, moisture was starting to invade them and so on. And all the other frescoes were in much better condition, but after the bombing were reduced to this kind of state. So for after the bombing, I mean, since the war was essentially over, the art historians from the center in Rome came and boxed up all the rubble, all the fragments of the frescoes, and they had all these boxes of them, and every so often they would open them, hoping they could do something, and then close them again in despair. And this lasted until the 90s, when they realized that maybe with computers, it might be possible to actually puzzle the whole thing back together. So they then did a large-scale photographing, very detailed photographing of all these frescoes, of all these fragments, both the front and the back. They were all numbered, and they digitized them, and they made them available to everybody who wanted to propose a way in which they could try to puzzle them back. Now, you might think it's an enormous jigsaw puzzle, but it was harder than that, because, well, they had an enormous number, 80,000, over 80,000 fragments, and they covered a whole area, almost 80 square meters, and the pieces were very tiny. But in fact, they covered only about 10%, less than 10% of the area that had been destroyed. Most of it was destroyed in rubble that could not be reconstructed. There were very few places where they expected that fragments would be contiguous. So it was like a jigsaw puzzle of which you had lost 90% of the pieces. And not only was it like such a jigsaw puzzle, but you also did not even did you not know where to put it, but you also didn't know in what orientation to put it. So they had, however, photographs prior to the destruction in black and white, but very high resolution, but of course with parallax of the frescoes. But the parallax they could correct for, because they knew exactly what the measurements were. So they had life-size black and white photographs of the originals, of these original over 800 square meters, which were printed out. And what they had was these tiny things. So it was like having a jigsaw puzzle, an enormous jigsaw puzzle with only 10% of the pieces, not in color. And you had the box, you had the picture on the box, but you had to place, for each piece that you had to find where to put it. And that was the big puzzle. And they asked for people to propose solutions. And in fact, the solution that was adopted was the one that was proposed by Massimo Farnasier, because it was the only one that seemed to give a way of dealing with this. And so the important thing was to find out where you had to put the fragments. So in order to explain what he came up with, let me say a little bit about images. So if you take images and you take a little fragment and you blow it up and so on, the image once digitized, which had been done to these frescoes, give you an array of numbers. A black and white image gives you, if it's an 8-bit image, will give you for each pixel a number between 0 and 255. 0 being all black and 255 all white, and then you have all the different shades of gray in between from 1 to 255, 4. So so you might think, well, that's easy then. You digitize both and you see where the numbers coincide. Well, it's not that easy, because if you rotate an image, then the numbers that you get for one look very, very different from just the numbers you got before. Also, if you translate the image by just a tiny little bit less than what a pixel would be, a pixel is a little average of what you see there, the numbers will look very different. So it's not so easy to identify that two pictures which to our eye look identical are in fact, once you digitize them, the same object, because the pixelations might be different. So what Massimo came up with was a way in which it was especially for the orientation that it was hard. So he came up with a way of representing the information in each fragment so that it would be easy to recognize it independent of orientation. So there are functions known to mathematicians that are called circular harmonics. And here a few of them are shown, with which you can represent anything at all. Anything at all that lives within a circle, even if it has no symmetries, can still be decomposed in a combination of these, because some of them have other symmetries than others. So you see here, there are some that have obviously, the third from the left on the fourth line has a threefold symmetry, while, for instance, the second on the seventh line has a fourfold symmetry. So combining these things, you can make resultant figures that have no symmetry at all. Okay, so here's an example of the image on the bottom right, reconstructed as a superposition of these functions. Every time an extra element is added, and you see as we have more and more of these different elements added, that they do build up to the image you start from. And in fact, we have a very simple rule for doing it. All these different images really do function as a basis, as different directions on which you can project. And so you can compute those projections and write that linear combination. So you can, if you give me an image, I can decompose it into those circular harmonics, and I will have different weights for all these circular harmonics. And then we know, once you have that decomposition, because the circular harmonics behave so nicely under rotation, we know exactly what any rotated version will look like by any angle. You give me the angle and I will immediately compute what coefficients I have to put in front. They're just, in fact, cosines and sines that I have to put in front of each one of those coefficients, and I can compute that from the angle you give me to find the representation of the rotated image. So that it's not a complicated thing to decompose something and its rotated version, and it's very easy to go from one to the other. And so that was used in the approach. So we're talking about the early aughts now, so computers were not as performant as they are now, where volunteers from universities and from departments would come in a central location where they had a few terminals to put in the manual legwork to give the manpower to, and you see these big terminals of the time, to go through all the fragments. So what would happen is that if you were a volunteer, you would pull up one of the as yet not identified fragments. You would then mark on it the largest possible circle that was completely within the fragment. It would decompose that circle, that image, and it would then compare it with at the right scale with a pre-computed database of the full black and white frescoes, where it had them only in one orientation, but it could easily compare with different orientations based on the one you had. So, and then it would come up with the 3 best matches. And so in this particular case, the top match actually is the right place, but you see there are other places that have lots of striations in them that could have been the thing that was recognized by the software in this image. And it had this human intervention in it. So looking at what the top candidates are and then deciding which one, because that actually made the algorithm much easier. It's much easier to make an algorithm that is that gives you few choices and you then finalize a choice than an algorithm that is 100% correct. So and in many applications actually people prefer the non-automatic, so a semi-automatic, something that reduces your choices and where then as a human you make the last choice. The art conservators actually trusted much more something where a human had made that last choice. That's a psychological thing, but it's also much easier to design such algorithms. And even now with machine learning, which didn't exist at all in any practical form in the beginning, in the aughts, it's often not possible to have that last little bit, that last fraction of a percent squeezed out. Okay, so they went over all the fragments that had something, because of course if a fragment was uniformly yellow then you couldn't say where it went, but anything that had something. And here you see, for instance, where the fragments went from this fresco. And here you have a detail of how closely it did indeed match the black and white. Here another place, another one. Now, just look at this. I mean, you might say, well, what do you know with this? Well, you know a lot. In fact, based on information like that, an art a conservator can reconstruct the whole image that we see in the red square here, because you have all the information about how the flesh tones were shown. You have the information about the tiles. You have the information about the leather of the sandal construction. You know the lance. You know the back of the shield. So you have, with a little bit of color, you can do a lot. Here's another fresco. And so in the church itself, they opted for, once they had all the fragments in the right place, for not repainting, but showing with big swaths of pastel paint what the whole composition looked like in color. And they left it in black and white in some places. Here you see other places were nicely reconstructed. I mean, here you see the scaffolding from when this was being done and the painting through it. And this is going to be an illustration of how you can reconstruct color. So we have the fragments on the left, but then from there you can try to start propagating color. And just like the art conservator does that by painting a little bit extra and so on, and then using the information they have together with their know-how, you can make algorithms that will do that. And so algorithms also can reconstruct. And so this is something that Massimo is working on now. It's an application where people would visit the church and would look with their smartphone and would not only see what you see in the search, but would also see an algorithmically reconstructed colorization.
Can I ask
so that
something?
was, yes.
Sorry, so this is just from a little bit back. When you said the way we solved the rotation issue is by using circular harmonics.
Yes.
But how does that solve the translation issue as well? Or how did they deal with that?
What they did with the translation, so I said that they would take the largest circle that was inherent. So once you decided on that largest circle, they had, because they had pre-computed a lot, so they would look at all the possible ways you could have taken a circle of that size over the whole fresco. And they had stored all the possible coefficients you had there. So they already had the translations in there. So they had just stored the outcome of taking a circle and then shifting it one pixel and so on and so on and so on. And the subpixel you can actually interpolate. So you would only need to go close and then try to find the right interpolation in between. And so what they would do is they would take for the circle they got, they would decompose, and then they would look at that decomposition and many different angular versions of it. And they would compare those to what they had for the full frescoes. And that's how it was computed so that it was still doable for people sitting there waiting a few seconds and getting an answer with the machines of that time. I mean, now the approach probably would be very different because, well, our computers are much more performant and image processing has advanced. But
yeah, thank you. Yeah, that makes sense.
But the important thing was to have a reconstruction, a representation on which that rotation could be computed so quickly. If they'd had to compute, because they would typically have something of, let's say, 128 by 128 to hold the circle. If they had to do the rotation, a matrix computation, to go to all the different possible rotated versions, then that with the computers of that time would no longer have been feasible. But decomposing in harmonics and then just doing something diagonal on all the coefficients and getting it back, that was doable.
Yeah, thank you.
Okay, so that was the first thing I wanted to talk about. The second one is a work that was done by Rick Johnson, and he originally did it together with the Van Gogh Museum, and then later it became used in many, many different settings, which actually, Rick Johnson is the person who got me into using image analysis technique, or developing tools using image analysis techniques for art historians and art conservators. So Rick Johnson himself is an electrical engineer. He's now retired from Cornell University. He worked his whole career on sound, on one-dimensional signals, but he'd always been very interested in art. And in 2005 or 6, he went to Europe and for a sabbatical year, and because he was so interested in art, jumped on the opportunity to get to know conservators at the Van Gogh Museum, and learned a lot from them. And he also was surprised that they didn't use image analysis more. Because he said use all this chemistry and all this X-raying and so on, but just plain old image analysis on the visual images. And they said, well, why would we? We're highly trained visual experts, which they are. I mean, it's amazing what they are attuned to. And he organized a workshop where they would let people who were participating in the workshop have access to the high resolution scans of Van Gogh data, which were kept very close to their chests. So that was an appeal to the image experts, that they would have access to this very normally inaccessible data set. But in return, we had to show what we could get out of it. And that was the start of my interest in these. And so, okay, here's a painting by Van Gogh. If you look at that painting and the top corner of that painting in X-ray and you enlarge it, then this is what you see. And you can see that it's an X-ray because you see all these nails at the corners. Those are the nails from where the canvas is hammered onto the stretcher. Something that's very striking is that you clearly see canvas structure. You see the weft and the weave of the canvas. Well, and you might wonder why that is, because after all, I mean, don't X-rays go straight through all that cloth? And of course they do. So what you see here is actually not the canvas itself. What happens is that canvas, certainly in the 19th century and also in the first half of the 20th century, would it's first prepared before a painter uses it, because if you didn't put something fairly impenetrable on it, then it would just soak up your paint and it would be very hard to paint and retouch and so on. So it would also take a lot of your paint, which is very costly instead of more moderate amounts. So these canvases are primed very often with a white background. And that was done typically with lead white, which gives a very beautiful white. It's also poisonous, which is why it's not used anymore. And of course, lead is something that doesn't let X-ray through. So if you have a canvas with its threads, and then you put lead white over it, then you will have in the valleys between the threads a little bit more, a little slightly thicker layer than on the hills over the threads. And so this layer of variable thickness of the lead white will absorb X-rays variably as well. And so what you see on the X-rays is that negative in the lead white of the canvas. And so some paintings have been what's called, well, had canvas in such poor condition that conservators had to put them down, and the cloth of the canvas can be attacked by certain types of paint or varnish or so on. So the threads were in such terrible condition that they would take the threads away. And then on this layer of paint, they would apply a new glue, a new canvas. So that's calling relining. And if that was done, then you didn't even have the original canvas, but the X-ray would still show you the original canvas because it showed you that lead white. Okay, so why is this of interest? Well, the Van Gogh Museum was making a complete catalog of all the known works of Van Gogh. And one thing they do is they write in it everything they know about when it and where it was painted, in what collections it has spent, and so on. And on the technical side, they put everything they know about the materials used, and they will also characterize the canvas. They will say it was a canvas of such a weave with this density on so much. So typically on the X-ray, they look in a certain number of spots and they count the number of threads. And this is an important factor in identifying, for instance, different periods in an artist's career, if they change their preference for what canvas they used and so on. So when Rick Johnson heard about this canvas and how tedious it is to actually count the number of threads per inch, he said, well, that's something that could be automated. And in fact, he did that then with undergraduates wrote programs and made them systematic and then tested it out on these paintings. And so what you do is you take a tiny little bit of it and you try to find at high frequency, because you look at several inches, and so you will have many tenths of typically a typical weave density could be 13 or 14 threads per inch if it's a coarse canvas, and it could be finer. I mean, 24, 25 threads per inch if it's a finer canvas. So if you have several inches, then you look at hundreds of them. So you look at the mathematical representation of that canvas, and you look at high frequency components. So you do at the Fourier transform, and you look at the very oscillatory frequency components, because those correspond to that light-dark transition in waves. And canvas is pretty regular, not completely regular, but pretty regular. So it lent itself well to that. And so they found, for these canvas structures, they found numerical ways of finding horizontal and vertical. Of course, it turns out that canvas is never really completely horizontal and vertical. And this is a canvas on which this is extremely pronounced. I mean, you really see the canvas kind of waving through. So it really deviates from horizontal in many places. This is not because the painter didn't stretch the canvas well before they started painting, but the priming itself is done on huge stretches of canvas, which are hung. And so it's very hard to hang those completely. So they have slight waves in them. And those are then kind of set in stone, well, not set in stone, set in primer. And the surface you get is a completely flat surface, but the thread itself in it may not be exactly on perpendicular horizontal and vertical lines anymore. And that's what you see here. So this particular canvas, when it was then analyzed, would give rise to 4 different pictures. So each one of the little colored blocks here is one little segment on which they did the analysis. And the 4 different pictures are, well, you look at one set of things where you analyze the horizontal threads, and one where you analyze the vertical threads. And for each of these 2 directions, what Rick Johnson looked at was the density, which was not completely homogeneous. These canvases were still, some of them were hand woven, some of them were machine woven, but not with the same regularity as fabrics now. So the density might change, and that's the image here on the top. It's the different density of horizontal layers. Then here we're looking at the vertical layers, but what we're looking at is the deviation of the thread direction from the vertical. And that is not homogeneous over the whole picture. And as often happens, when something new is possible, all of a sudden new vistas open. What they realized was that with these pictures, which gave them much more information because it gave information over the whole canvas instead of over just little pieces, they could look at fingerprints. They could view this as a kind of fingerprint of the canvas. And that actually helped them realize that some pieces of canvas were related to others. Van Gogh, like many painters, would buy canvas, primed canvas in large quantities, and then cut it and hammer it on stretchers for his paintings. And so these 2 paintings, the fingerprint of their canvas shows that they came from the same roll. They were what's called roll mates. And so these paintings, we now know that their pieces of fabric came from a roll in this way, because in one of those fingerprints, you see things line up like that, and in the other one, you see them line up like this. And so that then gave you where those paintings were on the roll. And that is, I mean, these paintings were actually from a period where Van Gogh shared a house with Gauguin. And so they actually can see that they share the same roll of canvas, which is a cool thing to know. But it can also have influence on in much weightier matters. For instance, there's a painting by in the Prado by Velázquez in the Prado collection. I don't know whether it's exposed, that had been de-attributed to Velázquez because, well, it was not as high a quality as some of the other paintings by the master, and they thought it was probably studio of. But when they did this thread count analysis, they saw that it was unquestionably from a roll of canvas of which all the other paintings were of the master. And also his studio typically could not share in the top quality canvas that he bought for himself. And so it's now be reattributed to him. I mean, it's just one of an off day. I mean, he was not the same. That makes a big difference to the quality of the price of the painting and the price of the insurance for the painting also. I mean, so a number of things have happened, and all this because we could Rick Johnson could make a procedure that was very tedious automatized, and that made it possible to look at much more data and made apparent certain patterns that had not been apparent before. Okay, so let's me then talk about this project that's going to be the remainder of this talk, which is a project on which I worked with the North Carolina Museum of Art, which has an incredible collection, of course, in it's not one of the top museums of the world, but it has, for instance, a beautiful altarpiece by Giotto. But the altarpiece, what I'm going to talk to you about is also an altarpiece, but much less famous, and I mean much less prominent. It's and I'll come back to that. I see that in my talk I have still a little bit about how other projects that I have done in art conservation and art history. I already told you that Rick Johnson is the one who got me into working on art history and image for art conservation. And the very first project I worked on was one in which we tried to distinguish styles and originals from copies, not by my choice, because it's my least favorite of all these projects on which I've worked, but because the Van Gogh Museum, in the beginning at the first workshop, they wanted to see what we could do. So they asked us this as a question. Usually when people encounter a new technique, it's not obvious. What can this be used for? And so they asked us this question. And what we did was we would analyze the images digitally and try to glean out information in order to compare different paintings. So a very, very quick overview. If you look at this painting, and it's digitized, of course, but imagine I blur it a little bit. I mean, since I had a whole table of numbers, I now have another table of numbers. I can compare them by subtracting those numbers. The difference is going to look like this. You probably don't see much, but maybe you see a bit more after I emphasize. I make every number 20 times bigger. And okay, so what I have lost are essentially very fine lines. And that's because when you blur, every fine line becomes a little wider. And so those are the pixels that have been changed. So let's do it on a very small piece of it, but you should imagine it everywhere. So I take a small piece and blur and blur and blur, and I have differences. Now here, the color that I'm showing you in these differences is just to emphasize what positive and negative and so on. It's false color. I mean, I'm still only comparing black and white images. So these three different differences that I showed you, fine, very, very fine to fine, fine to coarser, and coarser to quite coarse, have things in common. You see this edge of the clog occurs everywhere because that was a sharp line, and so very fine information lives at all scales. I mean, sudden transition is something that you see as you step back as well. But there are areas where there's nothing really at the fine transition. Something emerges and it goes away again. So some details live at different scales. So what you can then do is you can look over your whole painting and look everywhere where at what angles do the different scales emerge or recede as I do this type of analysis. And that will have some signature of how the artist used his brushwork. And so I have a movie. I hope that that's going to work, because sometimes doesn't want to do this. So let me. Okay. Okay. Ah, there it is. Okay, so here what we did is they gave us a whole different paintings of the Van Gogh Museum. And they asked us whether we could, based on our analysis, on the statistical analysis, distinguish from the others paintings that were not by Van Gogh, but that they had in their collection because they had influenced Van Gogh, or they had been thought to be by Van Gogh because he had them in his collection when, so can I restart this? No, oops, where is it? Okay, I'll have to restart it. GNOME. So when I'll try to talk through it, some of these paintings had actually been paintings by another painter called Bernard, who admired Van Gogh and with whom Van Gogh had made exchanges of paintings. So yes, they were in his collection, in his property when he died, but they had not been by him. And then there are a couple of forgeries. So there's one forgery here. It's going to come here. The one with this red dot where my mouse is pointing right now is a forgery from the 30s. So the red dots, they asked us, and indeed we could distinguish them. At the center, with our analysis, we made a virtual mobile, and the center of the mobile is where the median is, and the red dots are more or less at the boundaries, but not completely. You saw when the forgery came that it was hiding behind some others. I mean, so it's not as precise as you might think. It doesn't classify those are the Van Goghs and those are the non-Van Goghs. But still, this was one of the things that impressed it. What was more interesting is that talking about this made people ask us more questions. And this next one is a much more interesting question. This was the first painting on which X-ray fluorescence was used by Joris Dick and Koen Janssen, who proposed this, and you see it became the cover of one of the big journals in their field, analytical chemistry. So what is this about? This is a painting by Van Gogh. It really is, it looks like this, but if you look on its side like that, and you then take an X-ray, that's what you see. So there's a portrait underneath. Now, the fact that there's a painting underneath is not so, I mean, about 30% of Van Gogh's paintings have something else underneath, and many other painters do the same. Painting is something that you work at in order to try out different ideas, and so there are many things that are called studies. When you finish the study, you might feel that you have learned everything that you could learn out of it. It's like a scratch piece of paper. And well, you might use the scratch piece of paper for papier-mâché or for something else, or kindle the fire with it. Or in the case of a painter, since canvas is expensive, what they might do is put a new layer of primer over it, and it gives them a new canvas to paint on. So it's clearly what had happened to this painting. But then they were still interested in what was underneath, even though they're not interested in every other single one, what was underneath, but here in this they were, because it was a portrait from the time, it must have been a portrait from the time where Van Gogh was still living with his parents in the Netherlands, and he might have sent this earlier painting to his brother, Theo. Now, Theo and Vincent van Gogh had a lively correspondence their whole life, except when Vincent was living with Theo in Paris. And there's one letter in which he says, I've been doing experiments with a very dark palette with only very dark colors, in which I nevertheless want to give an impression of color. And I'm trying to see how that works. And I'm sending you with this letter a painting in which I succeeded particularly well. Now, the letter we have, but not that painting. And it was believed that most of those portraits Vincent van Gogh left behind in the Netherlands when he moved to Paris. But this painting was clearly overpainted in Paris. And it may well be that a painting where he valued especially what he could do before would no longer be of interest to him after he went to Paris and changed his manner. He encountered the Impressionists, and he became all about color. And as a result, it's not so unlikely that he would have overpainted it. So that's because of his assessment that this was one of the best of that earlier period. People were especially interested. So what Joris Dick and Koen Janssen proposed was to analyze this with X-ray fluorescence. So what you do with X-ray fluorescence is you take very high energy X-ray beams, which you bombard a tiny little piece of the painting. It excites, it ionizes a lot of atoms there, and they, in then getting back to the lower energy state, the ground state, they absorb a photon from ambient radiation, and that falls back into two steps. The first one, it takes some energy away, but then the next, it goes from one level in the atom to another level. And that, a new photon gets sent out. So sorry, they absorb electrons, and the electrons drop out, and as the electron drops, they send out a photon, and the photon has an energy, a wavelength that's exactly an indication of that energy step. And that energy step is characteristic for the atom that you're looking at. So by looking at the spectrum of the fluorescent radiation after this X-ray bombardment, you can see the prevalence of different elements in that little spot. And you can do that in many different spaces. You do that in one place, another, and so on. And that gives you then in the spectrum a pixelization of the prevalence of different elements. And this method is now used widely, but this was the first one. And these are that pixelization that you get in two elements where they saw a lot of information. One is asbestos, which was part of the vermilion that Van Gogh used. And indeed, you see it especially prominently in the lips. And one was antimony, which was part of his Naples yellow, which was the only light pigment he had on his palette. And so that's why it gives us a good idea of the luminosity, since he had to use it in order to give light dark impression. And so you see the picture most clearly, and that's the one that you saw now, in order to make that picture on the copy here, what they did is they used these antimony and arsine and a couple of others, and they colorized it, and that is what gave this this result. But then Joris came to us and he said, you know, we are analytical chemists. I mean, with interest in art, but we don't know anything about image analysis. Maybe you can do better. And so he gave us the raw data that gave rise to this colorization. And we had to do a number of things. So let me go to, I seem to be out of presentation, which is not what I wanted. So here. Sorry,
just to interrupt. I think you might have a Zoom window open on top of a presentation, maybe a chat or something. On the right side of your screen. Do you not have anything there? Oh, no, kind of top right, kind of a box. Is there anything?
Oh, that's a box, and I can do nothing about that.
Okay, because we can just see a black box.
I know, and there's nothing I can do about it. If you know how to do something about it, I please tell me. I've been teaching my whole semester with black boxes like that.
Yes. No, if you can't close it, then yes, I don't know. Sorry.
Yeah.
Mm-hmm. Yeah.
Okay, so let me go. And okay, so the first thing we found was that there were weird artifacts in the image. And so we asked them, and I said, yes, well, to do the X-ray fluorescence, we had to go to a place that had a strong X-ray source, which was a teaching hospital where they actually use the very strong X-ray beam to make short-lived radioactive elements. And those we can then, when they don't use them, the beam is redirected to this space where you can do physics experiments, because physicists help pay for this very expensive thing. And we reserved some hours on there, and we had our painting on a little sled, and it had to move whenever we went to the next pixel. But of course, as soon as the beam is needed for its day job, the beam is taken away and your whole installation has to wait till the beam comes back. And they had, in that arrangement, they had a slight synchrony problem. And since the thing was scanned horizontally, vertically like that, that caused for these artifacts in which you see this zigzag thing. So they know that in almost every line they have some breaks. They don't know exactly where they are. All they have is the results. And so we then had to first do a mathematical analysis of introducing breakpoints at the most likely things, so that all these big black blobs, which are caused by the impasto of the top painting, not letting the X-rays through as well, so that you have no signal there, became blobs again instead of zigzaggy. So we did a first run through and we did a pretty good job, but we actually are considering maybe going back to this data set to do a better job with more modern techniques. Then we inpainted all those blobs. Inpainting, how can you inpaint what you don't have information over? Well, of course you have information. You know it was a brush stroke. So you know the direction the brush stroke came before and after the place where you don't have information. So you can again extrapolate like we did for the color in the Fonazier application. So you mask it and you inpaint. And then we did the same with a different type of inpainting for the traces of these long stretches of grass. And then we had to do a correction on the eye. And we asked for advice and they said, oh, you use the other eye. We do that all the time. So we did that too, and we inpainted. So we had now a corrected version on all the different spectra for which we could do much more. And you see, it really is a detailed, very delicate reconstruction. So next, we took information. Well, we didn't have enough color information, but there were some colors on the palette by Van Gogh which just didn't show up in the spectrum because they didn't fluoresce in the spectrum wavelengths that they looked at. But what we did is we looked at some of the most and least contrasted paintings that he did in that period. And we realized that once you look at them, not in red, green, blue, which is the standard, but you try to extract luminosity and saturation and color wheel distribution. So this is just the chromants. And you remove the information that you get from the very dark pieces, because very dark orange or very dark purple or very dark anything looks like black. So you remove the black pieces. They actually were not that different. So that allowed us, with the partial information we had, to infer in chromants what the others had been and to then reconstruct. And that's how we got to this. So we got from the thing on the left, simple coloration, to what we got on the right, which made a big difference. Okay, so back to what we did with NCMA in my last few minutes. So they had in their collections 3 panels of an altarpiece that they knew came from the same altarpiece. And it's only in the 60s that they realized that a painting in the Museum of Portland, 3 in the Metropolitan Museum, a central panel in Chicago, all came from the same altarpiece. They could see that by details in technique that I may come back to. And when they discovered this, the curator at NCMA really was interested in getting an exhibit where they would all come together. But the other museums said, why? I mean, you still don't have a complete altarpiece. There's a panel missing. And I introduced them to Charlotte Kaspers, with whom I had worked for other projects, who is an artist, an art conservator, and she is actually an expert in what's called art reconstruction. She takes commissions from museums where she will reconstruct an art piece So make a copy, but with the same techniques as the original artist used. And so they commissioned her to make that missing panel. Now it was missing, they had no idea what it looked like. Well, but the other panels describe the life of John the Evangelist, and in order. And not only described his life, but they described it exactly according to scenes given in the Golden Legend, which is a book of which many, many, many collections in the medieval times had a copy. So that meant they could guess the missing scene, which had to be the baptism of somebody who had challenged John earlier to drink poison and so on. And so they could then make a composition that is certainly, if they ever find a missing panel, they will see that it's not the same. How can you reconstruct something you've never seen? But that would not have surprised at the time. And so here you see Charlotte working on that panel. It came out absolutely beautiful, gorgeous. The gold sparkled. The colors were brilliant. And that's when they realized there was no way they could put this thing next to the other panels, because it would be so shocking, and people would have eyes only for this shiny, bright new object, which was the only imposter. I mean, the other ones would have been wonderful, would have been authentic, and however wonderful this new one was, it was not the original. So what we did instead is we actually could, from studying the old ones and the new ones, and we knew that it was an exact correspondence because they had studied the pigments, and Charlotte had with new pigments made, and with the old techniques, something that was a new object. We could age, we could change the color on a virtual copy. They didn't want to do anything physical. They were not in the business of making a fake, but we could make a digital copy that we aged, and that could then be exhibited next to the other one. And so let me leave my talk here and go to the website. The exhibition has happened in 2016, and it stopped, but we have still a website. So it's duke-ipai.org projects GISI, where you can read all about this and much more. And you see here a reproduction of all the other panels and the aged panel, the virtually a printed out copy that we made of the virtually aged version of the new panel. And so there's a whole description here of everything, and you can see how there's a video of how Charlotte made that, which is all very interesting. And this is that aged copy. But once we had done that, we could, of course, also, if we could virtually age, we could virtually rejuvenate the other ones. And we did that as well. And for that, we had to be able to remove cracks, something that we had learned on earlier projects. We had to render the gilding. And in fact, in all this gold, you see there with punch marks that you see Charlotte use here, she used those techniques in order to put some relief in there. And that relief is how they actually found that these different paintings were of the same altarpiece together, because they all had exactly the same punch work. The punch work changes dramatically as the painting ages, because the gold starts becoming a little flaky as the whole painting cracks. So it's no longer gleamy, and there's no way you can polish it again. And where you had punch marks that gave something much lighter before, they fill up with dirt and they become little darker circles around it. So completely the opposite effect of what you would have wanted. So we made this rejuvenation. And so you can actually on the website go between the original panel and then the rejuvenated version. And the result of all this was that the exhibit became so much more interesting to such a much wider range of people, because there were kids interested in all this digital stuff and how can you do this, that from being a very specialized niche kind of event, it became an exhibit that attracted a lot of visitors, and docents adored it and would bring groups to see it. And so it was a big success event for the museum. And of course, the students, I worked on this with a bunch of undergraduate students who were absolutely delighted. And I'm going to stop here. I'm sorry I went a bit over time. You can find more about this last exhibit on the website. And
Okay, yeah, thank you so much. This was really interesting. Yes, now we have some time for questions. So yes, please do think of some questions to ask. I'll start off with a fairly general one, which is that, so kind of the broad mathematical techniques that you use for this, is it a kind of set of techniques that you're just thinking of new ways to apply them, or do you develop completely new maths for every new project?
It's a mixture of both. I mean, so the project itself will define to some extent what type of techniques we have to use. So with the biologists with whom I'm working, we are comparing in a very detailed way shapes of bones and teeth, so that they can use that quantifiable difference to test evolutionary hypotheses and so on. So there that almost tells you that you have to use differential geometry and computational versions of that and so on. So the problem dictates certain things. On the other hand, we like to use all the mathematics that exists already. So I always tell the students who work on a doctorate with me that whatever pure mathematics they can have time to study and have an appetite for, they should learn, because it can all come in useful. And so you try to know a lot of mathematics, so that when you have an application that calls for something different, something that hasn't been done yet, you can identify tools or approaches that could prove helpful. When I did my work on wavelets, I was really interested in understanding, in relating things that I had seen in signal analysis with new mathematical developments, and so that's what drove that. So I like very much talking to people in different fields and seeing what makes them tick and what problems they deal with, and see whether I can rephrase some of the problems they have as mathematical problems. And once I can do that, then I can try working on them.
Yeah, thank you. Does anyone else have any questions?
I do have one. I kind of missed how you were then using the scale of
So how does the scale come in? So we looked at what you see is you look at the detail information that you have to add or that you lose at every scale. You see how, for the case of the painters, you look at this for many different directions. I only showed it to you. I mean, I was not being angle selective where I showed it to you, but we can do this in an angle selective way. And you then can make a kind of statistic of, in this angle, things occur mostly between scales 3 and 4. in this angle, but on the other hand, there's a lot of detail. It emerges at all scales, or in this angle, and so on. So you make kind of a feature, a little table that characterizes the painter or his style during that period of his life, or his style on that painting, or and so on. So you do that then for every little piece of the painting, because we have these things with enormous resolution, and we do it on a 256 by 256 pixels, and we have thousands of pixels in both directions. So you have now a list with, let's say, 120 characteristics for every little patch. So you can then look at the painting is now represented by a kind of a point cloud in 120 dimensional space. And another painting is another point. And so you can then compare them by looking at how far they are from each other. And you parlay that into you then use multidimensional scaling to make the best possible visualization in 3D of that. And that gave us the mobile.
Okay. Hey, thank you. That talk was really interesting.
Okay. Okay. Any other questions?
Yeah, Luke Barrett has a question there.
Yeah, so you alluded to at one point how things have changed in the last 15 years.
Yeah.
I was wondering, how do you see things changing in the future with vastly greater computational power?
Oh, well, machine learning, especially in image analysis, has put us in front of a great conundrum, because there are some tasks on which many very smart people had worked very hard and had made progress, but not as much progress as machine learning techniques, deep neural nets have enabled to make us in the last 5 years, let's say. So it's very welcome to have that progress. I mean, it's wonderful. On the other hand, we have no good understanding about why it is so good at what it does. I mean, none. I mean, and many people develop a feeling for it. People develop a way of learning them, of getting intuition for it. And so people are exploiting them, as they should, for many applications. But, well, as a mathematician, I do believe that if we understood better why they were so successful at what they're successful at, we would be able to do much more even. I mean, because that's how it's always been. Once we really understand, we can use it for much more things. So that's really the big challenge right now, is trying to understand why are these darn things so good at it? I mean, and so good at what they're successful at, because you can try to use them in other contexts where then they're not so very good. So we also don't know about that. I mean, it's for the moment, it's just hit and miss. I mean, people try and work hard and so on, and sometimes it works and sometimes it doesn't. I'm not saying that people shouldn't. I mean, if something works for tasks for which you were trying to find a solution, then you should use that solution. But I think we also want to understand better what's going on. So that's a big, I mean, I hope well, it may not be done. I hope to still see the answer to that, but I certainly, if I were to fall asleep and wake up in 10 years' time, it would be one of the first questions I would ask. Have we understood why machine learning works so well? Why deep neural nets work so well? Not machine learning, why deep neural nets work so well? There's other machine learning that we understand very well.
Is machine learning already being used for this type of image analysis?
Sure. I mean, actually, I'm working with people in England at National Gallery in London and at University College in London and also at Imperial College. We have a group that meets weekly, and we actually met this morning. So a few hours ago for you earlier in the afternoon, but where we try to we try to develop and discuss techniques to, for instance, from dimly viewed images underneath a painting, get a better reconstruction of that X-ray. So if you have So yeah, there are altarpieces that are polyptychs, where you have doors that close and open. Those altarpieces have they're wooden panels. So when they on the door pieces, you have a painting on both sides. Those paintings on both sides, if you take an X-ray of the thing, which they like to do to assess where are areas on which things have been retouched and so on. Since the X-rays go through the whole thing, you see both your paintings. They know very well how to interpret paintings, X-rays of paintings, but of one painting. Now they have both. Now you can say, well, you could trace this must be from there and so on. Well, it's so tedious that you don't do it. And our eye is not good at separating those informations. So most of the time they cannot really use that information as well as they would wish to. So we have used both standard techniques supplemented by deep neural networks in order to split X-rays. And we can now do this very well. It's still challenging in some cases, but for some paintings we can do it very well. But now we want to go beyond that. We want to say, look, if we have a painting and there's another painting underneath, and we have the visual of the top painting, but we're not going to scrape off the top painting, so we'll never have a visual of the lower painting. Can we actually, out of the X-ray, remove the top painting? Which is a much harder task because we have no visual for the lower painting. But it's very interesting because if we could remove it, we could read the bottom painting much better. So for that also we're applying machine learning, deep neural nets. So yes, the X-ray separation, introducing a neural net really made the results much better. But so on the one hand, we are developing intuition of how to use the darn things, but that doesn't mean we really understand mathematically what they do, why they do it, why it has such good results, let's say.
Mm-hmm. Yeah, thank you. Yeah, that's very cool. Any other questions? If there aren't any other questions, then yeah, let us say thank you once again to Professor Daubechies.
Well, you're very welcome. And thank you for all hanging in there. So much beyond the original scheduled time. So, and I'll send you the slides.
Yes.
As well as a link to the website.
Mm-hmm. Yes, and I'll send them to everyone who attended the talk. Yeah. Mm-hmm.
Okay. Thank you.
Yeah. Then.
Okay. Bye-bye.